Hello, and thank you for joining us today. The discussion around acids and alkalis is a key knowledge for any cleaning operation. Without it, you'll be limited, you'll struggle in your career as a professional cleaner. Someone like a taxi driver who does not know how to change a punctured wheel, he'll make progress due to his knowledge of the road network, of how to take credit card payments, to be polite to customers. However, at the time that he has his first puncture, it all stops. My name is Everard Painter, the Managing Director of Actichem, and I'm looking forward to showing you just how easy and how simple pH, acids and alkalis can be, and how effective and efficient it can make your cleaning operation, saving you time, saving you money, saving you problems, and with all better outcomes for both you and your clients. So what is the pH scale? The pH scale is essentially a measure of the concentration of the hydrogen ion. When a solution has got a higher concentration of hydrogen ions, that is when it is on the pH acid side. When it has a concentration of the hydroxide ions, the OH, that is when we have an alkaline or a basic pH. So if we look at the acids, the dominance of the hydrogen ion, we can see there the hydrochloric acid, the sulfuric acid, the phosphoric acid, and the way that we've got those nomenclatures of them, you can see the dominance of the hydrogen ion. Then we go to the alkalis and we can see the dominance of the OH or the hydroxide ion, these ones that we're familiar with, sodium hydroxide, potassium hydroxide, ammonium solution. Now, putting those two together, taking the hydroxide ion and the hydrogen ion gives us water, H2O, water. So there we can see quite simply that a perfect balance between hydrogen and hydroxide gives us water, water being a neutral substance. Now, all solutions having a pH contain water, or the other way we can say it is everything that contains water has a pH, which also leads us to the next point, and that is where we do not have water, such as with our solvents, our non-polar solvents, there is no reference to pH. It's not that they're neutral, it's just that pH does not apply. These are things like your eucalyptus and limonene, then also your aromatic solvents and things like petrol, paraffins, etc. They do not have a pH. So if we have a look at the pH scale, quite simply, we can see that it starts in the middle. It doesn't run from 0 to 14. It starts in the middle at pH 7, which is pure water. That is neutral. Runs to the left-hand side, getting increasingly stronger on the acid scale, and then running onto the right-hand side, which is increasingly stronger on the alkaline scale. Now, these increase towards the two extremes of the pH table, as you can see, from your acids on the left, which is your strongest drain cleaners, battery acids, right through to pure water. Now, I want you to note a couple of things. One is that you'll note that most of your foods and your beverages are all on the acid side. Most of your cleaners are on the alkaline side. How important is it to know the pH of things? And I'll tell you why. Have a look at hand soap, liquid hand soap. It's got a slightly acidic pH. This is a reason why you will often find on a travertine or marble benchtop in an upmarket facility, a hotel, restaurant, what have you, and where the liquid hand soap bottle is sitting on the counter, there is an etch mark underneath it. And this is because the slightly acidic liquid hand soap is eating away at that very alkaline, it's a calcite substance, being travertine or marble or limestone, eating away at that calcite substrate. What typically happens, and I've come across this numerous times, is the building owner, the building manager will come and insist on the cleaner removing that stain. In actual fact, you can't remove that stain. It is an etch mark. It needs to be honed back. It needs to be taken out with a marble polish or something similar. But how many times have you tried to remove that stain, given the building manager the assurance that you can do it, and having to go back and admit that you can't do it simply because you did not know what was actually happening there, because you didn't have a handle on what pH and alkaline and acids were all about. So it leads me to the next point, and this is that whenever we come across a cleaning challenge, we need to ask ourselves three things, and we need to have a grip and a handle on three things. The first is the substrate. What is this? What characterizes a substrate? Is it sensitive to acids? Is it sensitive to alkalis? Is it not sensitive to either? Wool carpets, marble bench tops, all these things, they've all got a certain effect, a certain detrimental effect that can happen to them as a result of pHs. What is that detrimental effect? We need to know a lot more about our substrates and how pH affects them. Then we need to know about our soiling. What characterizes our soiling? How does the whole pH, acids and alkalis, seen have to do with the soiling that we were removing from those substrates? And then thirdly, our chemicals. Do I know what chemicals I have in my van, have in my store, are acids and alkalis? Can I go to every single bottle? Can your manager, can your supervisor, can your cleaners go to every single bottle in their cleaning van, in the store, and be able to name that it is an acid or a light acid or a alkali or it's neutral? If you can't as a supervisor, if you can't as a business owner, I'd honestly make sure that you can by the end of today. It is really important if you're going to be effective and if you're going to be able to overcome cleaning challenges and avoid making costly mistakes. So what we can then do to make this really, really simple is categorize our soiling. And this is what I'm first going to focus on, is the soiling into three categories. It's organic soils, and it's inorganic soils, and it's soils that are characterized by oil. So it's only three, easy to remember: organic soils, inorganic, or those characterized by oil. So let's have a look at organic soils first. Organic soils are proteins, carbohydrates, your body and food, oils and fats, your animal waste, your bacteria, molds and vegetation. These are all matter that once lived. That's an easy way to remember what an organic soil is. It's matter that once lived. You can also think of it as food going into the body and excretements coming out of the body. Now, this is both humans and animals. These are all organic soils. Where do we find them? Sports facilities, eateries, pubs, clubs. General grime is mostly made up of organic soils. And of course, your kitchen and food prep. Another easy way of remembering it: what dominates, what characterizes, what is the running theme through each one of those facilities that we've got on the left-hand side? It is where people are, people activity, human activity, or animal activity. We could have put in there, kennels and catteries. It's wherever there is living beings, we have organic soils, and they are characterized by being acidic. So very easy to remember: organic soils characterized by being acidic, and it's wherever living beings have been, we get organic soils. Now, to remove them, we use the opposite chemistry, and that is alkali detergents. Now, that is things from a pH from 7 up to 14. Now, to use an alkali detergent doesn't mean that it has to be a caustic or hydroxide. Sure, those are the strongest that we have, but there's also many others that you can notice on the SDS, on the product label: alkaline salts, builders, ammonia, ethanolamine, chlorine bleach. These are all chemicals which have an alkaline pH and are effective on organic soils. I simply refer to chlorine bleach just to make sure that you understand that chlorine bleach is an alkali. We typically don't use it on its own as a cleaner. I wanted to include it to make sure that you understood that chlorine bleach is an alkali, it's not an acid. Inorganic soils is matter that never lived. So how easy is that? Where we have organic soils as matter that lived, inorganic soils be matter that never lived. And inorganic soils are typically alkaline in nature. These are your limescale, efflorescence, rust, oxidation, minerals, etc. And these are all found where there is a presence of water. We need water to be able to carry inorganic soils, these minerals, either out of the substrate that has got wet from water, or from the water itself, which contains our hard water ions, limescale. So we find them in areas like toilets, bathrooms and showers, external surfaces, that have been rained on, or irrigation sprinklers. I've also added cement and grout smear as well. It's somewhat of a man-made inorganic soil, also strongly alkaline in nature. So how we remove them is with the use of the opposite chemistry, and that is acidic cleaners. So these are from pH 7 back down to 0. Once again, not every single inorganic soil needs the strongest acid on the shelf. However, we have a couple of categories of acidic cleaners or acidic raw materials: mineral acids, hydrochloric, phosphoric, sulfuric, etc. And in our organic acids, which are typically weaker acids, less aggressive and less hazardous, such as acetic and citric, oxalic, etc., glycolic. We typically use these a lot in maintenance cleaning, in showers and bathrooms, and also in the carpet sphere. And then we have the acid replacement technology, which is a very special technology, which is well worth inquiring about. The third one we have is where pH is not relevant, and this is oils and greases. It contains no water, and we remember from the earlier slide, if it contains no water, it's got no pH. So underneath this section, we've got our motor oils, waxes and resins, gum, bitumen, tar, inks, oil-based paints. This is where pH is not relevant. These are all things which do not have a pH. And the way that we remove them is with solvents. So solvents, once again, pH is not relevant. We have a couple of categories of solvents. Polar solvents such as glycols and alcohols. What's the difference between a polar solvent and a non-polar solvent? Easy way to remember it. Polar solvents is where a solvent is dissolvable in both water and oil. So think of it this way. We've got polar bears. Polar bears live in where there's a lot of water. So polar areas, water. So the polar solvents are solvents that are dissolvable both in water and oil. Very, very useful in our water-based degreasers. And then we've got non-polar solvents. These are things like xylene, toluene, paraffins, even petrol, eucalyptus, limonene that you cannot dissolve in water. They're only dissolvable in oils. And these are typically stronger. In dissolving things like oil-based paints and our hard gums and tars and some of our very old grease buildups. So the following page gives you a summary of it all. Lists down our organic soils, our inorganic soils, our oils and greases, and then the chemistry that removes them. We've got a couple of the Actichem products which are listed there, which gives you a very good overview as to how they fit into the story. And then finally, a couple of substrate warnings. Very, very important. And this is probably a subject for another webinar, is going over these various substrates and how acids and alkalis react with them. But there's a short overview just to keep you on track. Now, this particular slide, we will be providing you as a separate PDF so that you can print it out, copy it, have it on hand for yourself and your staff. Now, there's a couple of unique situations which I'd like to discuss with you, which are probably the primary reason I want to discuss with you is that it's actually just puts into very good illustrations of how this whole pH, acids and alkalis thing work. So the first one is in relation to urine. Urine is a very unique soiling. In the fact that it is an organic soiling, we know that organic soilings are acidic, and it is. Urine is an organic soil and it is acidic. We know that when we go into the men's urinals and they've got a marble floor, it creates pitting and these marks which can't be cleaned out. They can only be honed out because the acidic urine is eating away at that alkaline calcite stone. However, the trick to it, the unique phenomena to it is that as it dries, it turns to an alkali crystal. So as urine dries, as it ages, it turns to an alkaline crystal. Now that crystal is very robust. It encapsulates the bacteria within it, which is typically normally the E. coli bacteria. It also emits ammonia whenever it gets wet, wherever it gets moist. So when the urine alkaline crystal is dry, perfectly dry, it actually doesn't smell. The bacteria don't emit any smell. The ammonia within the alkali crystal does not emit any ammonia smell. We can be tricked into think that it's gone away. The pH of your alkaline urine molecule crystal is around the pH of 11, which is actually very similar to ammonia. That is why when you go into some of these animal areas, catteries, kennels, etc., or even into a very, very severely contaminated urine room in an aged care facility, for instance, you get that distinct smell of ammonia. And this is the urine crystal emitting ammonia. Now, you have to break down that crystal to release that E. coli bacteria, to enable to kill it and remove it, and also to neutralize its ability to emit ammonia. There's only two ways of doing it. There's one way of doing it, and that is with enzymes. Enzymes do take time and are seldom effective for the quick go in, fix a problem, and walk out story that we find with many, many carpet cleaners or restoration people. They're normally used by people such in aged care facilities especially, and homeowners and people that own catteries, etc., where they can afford the wait time. Very, very effective. However, the other way of doing it is to take the acid and alkali side, where we've got an alkaline crystal and we use an acid to dissolve it. So we use an acid to dissolve it. Being an alkaline crystal, we use an acid to remove it and it dissolves it, and we have a result within a few minutes. That neutralizes its ability to release ammonia. It also releases the E. coli bacteria to be simply flushed away. We can follow it up with a disinfectant to kill any remaining bacteria that may still be existent. Wet area cleaning is another one that is very, very interesting. This is where we have both human activity and water. We know with human activity, we have organic soils. We know when we have water, we have inorganic soils. So have a look at the situation. We have showers, aquatic pool surrounds especially. They will contain both water and human activity. So should we be cleaning with an acid or should we be cleaning them with an alkaline? This This is where we need to do a little bit of forensics. We may have to do a dual clean. Clean with an alkaline first, followed by an acid. Always do it in that order. Always an alkaline, then an acid. That dual cleaning required will normally solve the problem. However, if we do a little bit of analysis in it, let's take, for instance, showers in a change room block. We have a bunch of teenagers running around for 2 hours playing basketball. They jump into the showers for 2 minutes and off they go. What is the dominant soiling in that shower? We've got wet, plus we've got a lot of sweaty humans going through there, which means a lot of organic soils, perspiration, body fats, body oils. The likelihood is that an alkaline solution is actually going to clean those showers better than an acid because of the dominance of the organic soiling. So we need to be a little bit forensic sometimes. So what may work on one application using an alkaline may not necessarily work on another situation because the soiling is different. We've had situations where in change room shower blocks where the acid cleaner wasn't working. So they go down to the store and they get a stronger acid cleaner and they get a stronger acid cleaner, or vice versa. They were using an alkaline cleaner and it's not working, so they go down and get bleach, and then they go down and get a floor stripper. You're just using the same pH side of the side of the pH scale to try and clean that solution. You need to swap the chemistry across from an alkaline to an acid or an acid to an alkaline if your cleaning is not working. And typically speaking, 99% of the time, you'll achieve a result. Now, the last one is our pre-clean tiles. This is a situation where we have tiles that are cleaned day in and day out, right from Mrs. Housewife, who's using a neutral detergent, using a Disso. They all contain a certain percentage of alkaline builders. Even if your pH is right down at 7.58, there's still a percentage of alkaline salts being used there. Right through to your situations in shopping centres, in busy shopping centres, busy commercial buildings, where they're using an auto scrubber with an alkaline salt dominated cleaner, and the whole time we are leaving a certain amount of residue on the floor. They will come along and try and clean it with a floor stripper with bleach because the tiles are slowly getting more and more dirty and they cannot remove it. Just switch across to an acid cleaner and you will find it will dissolve those alkaline residues immediately and the floor comes clean very, very quickly. You can reverse years and years of alkaline residue in simply 1 or 2 cleans with a correct acidic cleaner. So thank you very much. That brings us to the end of our webinar this morning. We certainly would look forward to your questions now. And we also would like to ask that you suggest any future topics for these webinars. So if you found them useful, please send us through some suggested topics and jump online, and also make sure that you've downloaded or put in your application for one of these printed brochures. They've become incredibly popular. Users finding them incredibly useful just in their everyday cleaning operations and for their technicians especially. Thank you very much.